Hey there, Physics 30. We're going to wrap up Chapter 14 today. What you should have already done is you should have already read through this end-to-end anticipation guide. We're going to talk about the wave-particle duality and Heisenberg's uncertainty principle. This is probably the one lesson that I'm really unhappy that we can't be together and have a discussion about it. So I'd like to talk about it on Thursday here. This is where physics gets really weird and super cool, and it leads to kind of this idea that the more we know, the more we learn, the more we realize that the less we know, right? So you should have already watched this video, okay? This guy, and I know he's pretty cool, but it it leads to this idea of like how do electrons, right, light acting as a wave and a particle kind of makes sense because light is special, right? Light seems special. Now at the time it made sense. Everyone's like, okay, well light's special, so good. The problem is that De Broglie here, Lou De Broglie, he basically said, well, if light, which is essentially a wave, can act as a particle at certain times, then what about a particle? Can it sometimes act as a wave? Right? And so he thought, well, I'm going to try and pick a very small particle. And so he picked electrons. And that led to this idea is that but he was, again, thought he's crazy. And so it's like this idea that particles and waves are kind of interchangeable and they depend on how we observe things and all that kind of stuff. And so one of the most interesting things, and if you read about the Heisenberg uncertainty principle, is you realize that observation, by observing, we actually change the very nature of the way things behave, right? Electrons know if you're watching, and it's baffling. It's this crazy concept, right? Okay, but I can get more into that, and we're going to talk about it as a class as much as we can. I really suggest you guys jump in on Thursday and kind of get your head wrapped around some of those concepts. All right, so De Broglie shot electrons through a double slit, and he observed an interference pattern. Okay, so interference pattern, right? So first of all, we think this. Electrons, they're obviously particles. Okay, electrons are obviously particles, right? But then we'd hit an interference pattern. Get an interference, which tells us they are a wave, right? So what that tells me is that electrons are both a particle and a wave, right? Well, if electrons are both a particle and a wave, then why isn't a proton, which is a little larger? Why isn't an alpha particle, which is a little larger, right? Why aren't they considered particles and wave twos? And what actually De Broglie basically said is that everything has a wavelength. Everything is a wave and a particle. So things behave like particles and waves, and that's kind of this thing we just have to accept. And that does not sound like fun, right? So of course he does some math and he basically says, well, everything has a wavelength. It's based on its momentum, right? It's based on its momentum, and P equals mv, and put this equation together, and we can kind of simplify that De Broglie wavelength is lambda equals h over mv. Now this is not in your formula sheet, okay? But it's putting together two equations, right? Two equations, right? But it's kind of the idea. Okay, is that you have to put two equations together, and that's what this whole chapter 14, 15, 16, 17 are really all about, putting a bunch of equations together. So an electron is accelerated from rest by a potential difference of 150 volts. What is the De Broglie wavelength of those electrons? So I started by stating the De Broglie wavelength equation, right? So I started there. I realized that I have h and I have m. I know that's always a constant. That's Planck's constant. I know the mass of the electron. What I don't have is the velocity, right? So the first step I have to do is find the velocity. So I go back into my, tool chest of tricks, and I notice that I have this equation of electricity and magnetism that says V equals E over Q, right? V equals E over Q. So I rearrange that, and I find that E equals VQ, right? V being volts, not velocity. Use the volts, right? Use the charge, and I get the energy of this is 2.4 times 10 to the negative 17 joules. Great. Use that energy to then solve for the velocity. There's a V under here in case you can't see. use energy to then solve for the kinetic energy and then put the numbers in and solve for velocity. So the velocity I get is 7.258743, right? So 7 times 10 to the 6. Pretty fast, but not the speed of light. Then I can use that number right here, okay? Use that number right here, and it gives me my wavelength. So it tells me my wavelength is 1 times 10 to the negative 10 meters. So, 0.1 nanometer, right? So it kind of gets me in that, ultraviolet range to an X-ray range. And what we actually find is that electrons actually emit X-rays when they move really fast. And that's pretty cool too. And so that's all related to this. And so we get there's this kind of idea that an electron has a mass and a velocity, but then it also has a wavelength. So it's actually a mass moving like a wave that actually is a mass. And it kind of is confusing, but we start to realize that these are overlapping concepts. And so the idea is that every single thing that has a mass and a velocity has a wavelength. And for an electron, that's a significant wavelength. That's quite large in comparison to the size of the electron, right? Electrons aren't very big. So what that leads us to is thinking, well, why don't we notice things acting like waves? Like why doesn't my skin move like a wave? Why doesn't my skin interfere with each other? Why does it hit instead of interfering? Well, the reality is that the larger the object, the greater the mass, the less it matters, right? The less the wave part matters and things act like particles. The more they become like particles, right? So, for example, if we take a baseball, 145-gram baseball, diameter of 10 centimeters, leaves about the speed of 38 meters per second, right? So we can calculate the de Broglie wavelength of this, right? So I use that equation, and the de Broglie wavelength is 1.2 times 10 to the negative 34 meters, right? So we're not talking about a nanometer. We're talking not even an attometer, which is the smallest on Earth. It's like we're way down there, right? We're in the smallest realm of length, right? Think of a meter stick broken up into like multiple quadrillion things, right? Sections. That's how long we're talking about. And so in comparison to the diameter of the baseball, which I just turned into 10 centimeters into a meter, right? The diameter of the baseball is 8.31 times 10 to the 32 times larger than the wavelength. So we're never going to notice, considering that our eyes can see the baseball at a certain size, 10 centimeters, we can see that very easily. This really small number here is never going to affect how it works. So the wavelength can't affect those things. So when two baseballs collide, their mass, their size, overrules their wavelengths. They don't interfere. So at a certain point, things stop interfering, right? Their wavelengths just aren't enough to cause interference patterns or anything like that, right? Okay. And so what this leads us to is, and this thing doesn't work, but it kind of is the idea of the wave-particle duality. Okay. The reason it says duality is because things are not waves or particles. They're both. Okay. They are both simultaneously at the same time. Okay, they're both. This is also known when something's doing two things at once that shouldn't happen. It's called superposition. Okay, superposition. When you watch that little animated video, right, they had the two slits, and all at the same time, the electron didn't pass through, so it passed through one, or passed through the other, or passed through both. All of those things actually happened all at the same time. Okay, they were in superposition. They were all happening. Even though it doesn't make sense, they were happening, but they were, because they're not particles, right? They're also not waves, right? If it was a particle, it'd always only go through one or not go through at all. If it was a wave, it would always go through both. But it does everything, because it's both a particle and a wave. It's particle-wave duality. It's both, all right? Okay, and so this kind of idea, and so the way we view things, right? We used to view this is the nucleus, and the electron would go around like so, and we would notice. But now what we do is we view this, and then we have just basically a cloud around the particle. Okay, the cloud around the nucleus. All right, and the cloud is most dense in the center. right? And it's the least dense far away because the electron is most likely near the center and less likely farther away. And this has to do with Heisenberg uncertainty principle, which accounts kind of for observation, right? So Heisenberg's uncertainty principle is basically that I can know where something is, or I can know how fast it's moving, but I can't know both. At least not enough that I can actually, like with a car, that's easy. You can know exactly where it is and how fast it's moving because its wavelength is so small. But with an electron, right, if you want to know exactly where an electron is, you won't be able to find out how fast it's moving because of this wave particle duality, right? And so what we get is that and the reason is because if you want to observe an electron, right? If you want to observe an electron, well, how do we observe things? Well, we throw stuff at it, right, and bounce it off, and it comes back, right? When I see the wall, it light hits the wall, and light comes to my eyes. Makes sense, right? The problem with an electron is if I throw a photon at an electron, trying to figure out where it is, when that photon comes back, it actually moved where the electron is. It hit the electron and caused the electron to move, right? It'd be like trying to fix a car by driving another car into it, right? So yeah, your car's not moving and someone comes and hits you with their car. I mean, yeah, like your car will be moving, but you're also going to cause damage, right? You're going to change the makeup of the car. And so that's that uncertainty principle, right? And so this is kind of the idea is that this is all coming together and we're realizing that these small particles, electrons and smaller, behave so strangely. And so we get to the wave particle duality of light. Light is neither particle or a wave. Our interpretation of the nature of light depends on the instruments we use to study it. So light is just hanging out both a particle and a wave, right? Doing both. And depending on if I have a double slit experiment or if I have a photoelectric effect, right? Photoelectric effect or a double slit experiment where it creates an interference pattern, we tell it if it's a wave or if it's a particle. We tell it if it's a wave or a particle. So this is my favorite little drawing right here, this guy. That's one of my little favorites because it's really both, and it depends on how we look at it, right? If you really focus on the large picture, right, light is a wave. But if you look at each individual letter there, it says particle, right? And so that's the thing, is that it kind of depends on how we observe things. And so the idea is that by merely observing or performing experiments or telling things to do it, we are affecting quantum mechanics. And so this leads to a lot more difficult understanding of the universe and how these things interfere. And if you think about it, in order to build a Lego structure, a big one, let's say you want to build a Lego structure, the size of your bedroom, right? Well, you have to start by understanding how each individual Lego fits together. And what we've now learned is we don't really know how they all fit together, right? And people, scientists have been studying this and putting math towards it, and we have a decent understanding of how things work. But why they do these things is still pretty. It's not really effectively known, right? It's just our best ideas. All right, so that leads us to the end of this chapter 14. This is probably the most difficult lesson in physics 30 to get your head wrapped around. As we get into chapter 15, 16, 17, we're going to review some more of this stuff, okay? I strongly recommend that you guys check these videos out, see how she goes for you. Alrighty, have a good one.